Okay, this is Math 105, Section 2.3a. We'll talk about kind of getting more information from functions by looking at graphs. Okay, so we'll see how a graph tells us whether the values of the function are increasing or decreasing, and also where the maximum and minimum values of the function are. So sometimes algebraically, we can't always tell, or maybe looking at just the rule of the function doesn't really tell us, but if we look at the graph, we can get much more information from the function. Okay, so just keep in mind that a complete graph of a function contains all the information about a function. It tells us which input values correspond to which output values. Okay, so keep this in mind. The height of the graph is the value of the function. That's the key there. When we talk about the value of the function, we're talking about the y, which is the up and down, or the height. Okay, so for example, here's a graph of the function capital T, which gives the temperature between noon and 6 p.m. at a certain weather station. So our x is the time. Noon would be 0, 1 for 1 p.m., etc., up to 6 p.m. So the temperature is the height of the graph. So you think the time at noon is 0, and the temperature is 15. So that'd be T of 0 is about 15 degrees. I'm putting approximately equal to because we're estimating from the graph. The time at 1 p.m., T of 1, would be about 25 degrees Fahrenheit, between 20 and 30. And then the time at 2 p.m. would be about 37 degrees Fahrenheit. And that looks like it's the highest temperature that we have between those 6 hours. You can see the temperature is going down. So we're talking about the value of the function. We're talking about the height of the graph. Okay, the temperature is the height of the graph, how tall this is. Okay, so let's answer some questions about the graph. T of 1, T of 3, T of 5. Which is larger, T of 2 over T of 4? And find the values of x for which T of x is 25. And find the value of x for which T of x is, I believe that's less than or equal to, but we'll come to that. Okay, so T of 1 is the temperature at 1 p.m. And we already looked at that and we said T of 1 is 25. You look at the height of the graph. T of 3 is about 30. And then T of 5 is 20. So what we're doing is we're going to the 1, 3, and 5 on the x-axis and seeing what the height is to get the 25, 30, and 20. Since the graph is higher at x equals 2 than at x equals 4, then T of 2 is larger than T of 4. Okay. The height of the graph is 25 when x is 1 and when x is 4. Okay. So the temperature is 25 at 1 p.m. and 4 p.m. Okay. And the graph is higher than 25 for x between 1 and 4. In other words, the temperature was 25 or greater between 1 and 4 p.m. Okay, so just going back to the graph there, we can see T of 1 was about, we said it was about 25. T of 3 was about 30. I know it's kind of small there. T of 5 was about 20. Okay, and then we looked at T of 2 versus T of 4. So T of 2 we said was about, the highest, which is said about 37. And then T of 4 we can see is lower. So T of 2 is greater than T of 4. And we were seeing where the height of the graph is 25. So if we go through 25 between 20 and 30, we can see that happens at x equals 1 and at x equals 4, or 1 p.m. and 4 p.m., where the height is 25. Okay. And then we said where the graph is higher than 25, and that's between x equals 1 and x equals 4. So we just draw a line across at 25, and we see where it's higher, and it's between 1 and 4 for x, for the hours. Okay, domain and range. Remember, domain is the set of all inputs, and range is the set of all outputs. So if we're looking at a graph, we can kind of look at where the graph is horizontally, where the graph exists horizontally for the domain. So here the domain would be between this point and this point, okay, on x. And the range, you can see where it exists vertically. Now it can overlap vertically, that's okay, it's still a function, it's still passing the horizontal line test. So it's okay that it's doubling up on the range, but the range would go from down here to up here, okay? So remember we talked about in class that, let's say I'm the little arrow and I'm walking along the x-axis. I don't start to see the function until I get to that first dotted line, and then it keeps existing until I get to that second dotted line on the x-axis. So that would be my domain, is that blue area. And then for the range, I'm going to walk up the wall. So I'm going to go up the y-axis and I see where the function starts to exist. So when I get to this dotted line along the y-axis, that's where it starts, okay? and then I keep going, and then it stops up here, right? So that would be where the range ends. Okay. Now, if there were a gap in here somewhere, let's say there was, then I would take that part out of my range. So if you have gaps either horizontally, you would take them out of the domain. If you have gaps vertically, you would take them out of the range. Okay, let's look at an example. First, we actually don't use graphing calculators in this class, but I'll actually use a graphing application to look at some of the graphs from section 2.2 on Monday probably. But let's just look at the graph of this, and then we'll find the domain and range. So now this is actually, if you think about, this is kind of before we graph this, let's think about this. This is y equals square root of 4 minus x squared, right? And if I square both sides, I get y squared equals 4 minus x squared. Okay, and then I can write it like this, which is a circle with a center of 0, 0, and a radius of 2, right? Because this would be x minus h squared plus y minus k squared equals r squared, right? But this is not the full circle, okay? This is only half the circle. This is the positive part of the circle. Because if I went back with this equation here and I solve for y, kind of go back, I would get this. I would get y, oops, sorry about that. I would get y equals plus or minus the square root of 4 minus x squared. So this equation is half the circle, okay? It's like this. Center of 0, 0, radius of 2, so it goes like that. Okay, goes to 2 here, goes to minus 2 here, and then we have 0 in the center. Okay. So we want to find the domain and range of that. Okay, so we can kind of see what domain and range is going to be, right? Minus 2 to 2 for domain, and 0 to 2 for range. But let's look at the graph of that. Okay, so here's our graph of that, and we can see the domain. It starts at the function starts at minus 2 for x, and it keeps going, and then it stops at plus 2. So our domain is minus 2 plus 2 interval, including the endpoints, okay? And the range is 0, 2. So notice the range as we're going up the y-axis, it starts at 0, it's to the left and right, it's on both sides, and then we get up to 2 when it stops, okay? So just keep in mind, this is the half circle, this is the positive part of the half circle, okay? Positive part of the circle, x squared plus y squared equals 4. Okay, so there's our range 0, 2, including 0 and 2. Okay, it's also important to know like where a function is increasing and decreasing. So we can think about as we move along with x, so x is increasing as we go to the right. So what we can say is when a function is increasing, as x increases, so does y. So in other words, they're both going in the same direction. X is increasing, y is increasing. And you'll notice on the graph that you're going up a hill. You're going uphill when you're increasing. Okay. And then when you stop going up a hill, you're no longer increasing. Now you're decreasing as you go down the hill. So between little a and little b on x, this function is increasing. Okay. Now it's going downhill until we get to that capital C. So between little b and little c on x, that function is decreasing. Okay. And then it starts going uphill again. Okay. So between little c and little d, it's increasing again. So here's an interval AB where it's increasing. You can include the endpoints, but you don't need to because technically it's doing neither or both on the endpoints. Then between C and D, it's also increasing. We're talking about intervals on X. And then finally, F is decreasing on BC, between little b and little c, where it's going downhill. So we just kind of trace the function and see if it's going uphill or downhill, and then mark off the intervals as increasing intervals or decreasing intervals. Okay, so we can say that a function f is said to be increasing when its graph rises and decreasing when its graph falls. Okay, and then our formal definition is this. Okay, f is increasing on an interval I. We'll call it capital I, some interval. Now we're saying whenever x1 is less than x2, in other words, x1 is to the left of x2, so we're going this way, left to right, in our interval, and that means the y's go from smaller to larger. Okay, so the y value here at x1 is going to be smaller than the y value here at x2. Okay, so basically we're saying as the x's increase, so do the y's as we go left to right for x's. You know, that's what x is increasing means we're going left to right. Okay, so as we're going left to right, we're going up. And that's true. As we go left to right, the function is going up. Okay. Decreasing is just the opposite. We still have x1 less than x2, so we're still going left to right. Okay. But as we go left to right, our y's are going down. In other words, this y at x1 is bigger than this y at x2. The f of x1 is bigger than f of x2. So as we go left to right, the function is going down. The y's are going down. Okay. But that's, you can see that they're the opposite direction, right? Here, x is increasing and y is. Here, x is going up and y is going the opposite way. It's going down for a decreasing interval. Okay, and you can see that pretty easily on the graph there. Okay, so let's look at an example, and here we're actually looking at a graph that we don't really know how to graph yet, but we'll use a graphing calculator for this. But this actually has a degree of 4, right? The highest power of x is 4. So let's look at a graph of this, find the domain and range, and find the intervals on where f is increasing and decreasing. You know, on a test we're looking at this, I won't have you graph something like this. I'll probably just have you give you a graph and have you find the domain and range and look at where it's increasing and decreasing and look at the intercepts and things like that. This is for section 2.3. Eventually we'll be getting to a point where we can graph this sort of function, but not yet. Okay, so here's the graph of that function, 12x squared plus 4x cubed minus 3x to the fourth, and we can see it's not just a parabola. It's got a couple curves there, you know, and then it goes up and curves around, then it goes back down, and you know we do have end, you know, it doesn't have endpoints here. It just keeps going in both directions down. Okay, all right. So there's the graph of that. Okay, so here's our graph, and then we'll look at the domain of f. Remember that this keeps going down. I'll write those again. That this keeps going down like that, and it keeps going down like this. So the domain is going to be all real numbers, because as you're walking along the x-axis, that function's always going to be there. It'll be way down here, way down below when you're over here. It'll be way down below when you're over here, but it's still going. So that domain is all reals. Okay. We're not going to worry about using the trace feature on the graphing calculator. You can do this if you want, but we don't do this in class for test or anything. But the highest value of this is about 32. Okay, so we can say the range. Now the y keeps going down, right? So the y goes from minus infinity up to 32. So that's 32 there. Okay, about 32. So the range is minus infinity to 32 bracket, because it actually does reach 32. Okay. Now let's look at the intervals where it's increasing. Now it's increasing, we're going left to right, remember, so it's going up from negative infinity, so it's increasing until we get to about this point, okay, on the x, which is, look at our scale, that's minus 1. Our tick marks are 0.5, so this is 1, this is 2, this is 3, this is 3.5. So if we go backwards, minus 1 is that tick mark there, okay, 2 tick marks in. So it's increasing from minus infinity to minus 1, okay, and then it stops, okay, and then it's decreasing from decreasing from minus 1 to 2, okay, so it's going down again as we go from x. So this is where our minus 1 is, kind of right there, okay, on x. So it's increasing, you know, coming from minus infinity up to here, from minus infinity to minus 1 on x, okay. Then it's decreasing from minus 1 to 0 on x, okay. We're talking about on x, so. And then it starts increasing again until we get to about 1, 2, until about 2, okay. So I'll put the 2 there. There's 2 there. So you can see it's kind of increasing as we go from 0 to 2 on x. That function is going up, okay. And then it's decreasing again as we go from 2 to infinity. So now it just keeps going down as we go from 2 to infinity on. Now we're talking about on x. So from minus infinity to minus 1 on x, that function's going up, okay. From negative 1 to 0 on x, that function is now going down, okay. From 0 to 2 on x, so from here to here, that function's increasing again. And then from 2 to infinity on x, that function's going down. Now we didn't say anything about how high up or down we're going. These are just intervals on x where it's either going up or going down, okay. Okay, a lot of times for applications, we may want to find the largest or smallest value of a function. Um, so let's say we're looking at a function that represents revenue profit. We may want its maximum value, okay? Or maybe we're looking at something that represents cost. We may want to find its minimum value, okay? So we can find these values from the graph. Okay? But let's talk about the concept of local maximum, local minimum first, okay? Local maximum value means that at some x near A, that some x point A, okay, that y value, f of A is the y value, is bigger than or equal to all the y's near it, okay, when x is near A. So kind of think it's like the highest y value in its neighborhood, okay? So we have a local maximum here, okay? And we also have a local maximum here, okay? Because it's the highest y value in its neighborhood. And by neighborhood, I mean you could look at like a viewing window of a graphing calculator, kind of like that or like that. We could just zoom in on that, and we can see where the highest y value happens. It happens right here, and it would be at this point. So this would be where our A might be. Okay. So let's draw that in there. Let's say this is our A. Okay, there. Okay. And that would be our local maximum there. Okay, so we have a local maximum here at A, and we have another local maximum at this point. We call it B or whatever. Okay. Local minimum is just the opposite. That's where when we have a local minimum at A, that means the y value at A is less than or equal to all the y values near there. Okay, so f of x would be the y values for x near A. Okay, so that would be like the bottom of a hill. Okay, so this is a local minimum here. Okay, at this point, and there's a local minimum here. Again, we're just kind of zooming in, with our graphing. Think of it like you take your graphing application and zoom in. So this would be the lowest y value in its neighborhood. That would be the lowest y value in its neighborhood. So that's what we mean by local minimum. Okay, so it's kind of in a specified area. Okay, so we would have a local minimum. Let's say, let's label these. Okay, so let's call this B. Okay, this x value be C, and this one will be D. Okay, so we can say we have local maximums at A and C. Okay, based on these. So local maximums at A and C, and the actual local maximum values are the y values. And then we can say local minimums at B and D. Okay, where this is our A, right? And this is our C. Okay, and this is our B, is the x value, and this is our D. Okay, so these are the x values here. When we say at, we're talking about the x values. Okay, the actual local minimums and maximums are the y values. Okay, and this is just kind of reiterating that we can find using a graphing calculator. We could say use a viewing rectangle such that the point AF of A is the highest point on the graph of F within the viewing rectangle. Then that number is a local maximum. Okay, so if we're doing this as our viewing rectangle, then the local maximum would be at A there. Okay, if we're doing our viewing rectangle here, then our local minimum would be at B there. Okay, we're just zooming in on parts of the graph to find that local minimum, local maximum. Okay, but again, you can think of it this way: local maximum is just the top of a hill. Local minimum is just the bottom of the hill. Okay, let's look at another example. Here we have a cubic function, f of x equals x cubed minus 8x plus 1. Again, we shouldn't have to know how to graph this yet in section 2.3, but we will soon. So this is our graph. Let's say we use a graphing calculator, and again we have the arrows going out, keeps going up, and this keeps going down. Okay, and notice we have looks like we have an x-intercept and a y-intercept at the origin, or near the origin anyway. Okay, local maximum. So we have a local maximum. Looks like it's about x equals minus 1.8 or so, and we have a local minimum at about 1.5, 1.6 for x. So just kind of zooming in on that left, the hill, you can see it's between 1.6 and 1.7, about minus 1.6, 4 or so is where our local maximum is. And that local maximum value is about 9.71, close to 9.71. Okay, would be the actual value of the function. And if we used a graphing application, we'd get, trace, for example, on a graphing device, we'd see the y is 9.709 and the x is minus 1.633. Okay. And then similarly, we can do for the local minimum. So we go to the place where it's going to the bottom of the hill, and if we do a little trace with our graph, we can see that the local minimum is happening at about 1.63 or so, 1.64, and that local minimum value is about minus 7.71 or so. Okay, and this is exactly what it is, minus 7.709, and this would be an equals here. 1.633. So, we'll look at graphs on tests and quizzes that are a little, we don't have to zoom in so much, we can kind of figure it out based on the graph. But just remember that local minimum is bottom of a hill, local maximum is the top of the hill, and we say it occurs at some x value. Okay, and the actual local minimum or local maximum value is the y value.